Begin. First off, good afternoon. I'm Jason Thomas, project engineer at America Makes, and your host for today's America Makes TRX webinar series. A little background on the TRX webinar series before I introduce our speaker. As America Makes continues its mission to expand and accelerate the footprint of additive manufacturing and 3D printing, this medium, called the America Makes Technical Review and Exchange webinar series, was created. By creating this platform of the additive manufacturing and 3D printing community to come together and share knowledge and experience with the broader community. If you or your team are interested in presenting during the TRX webinar series, there will be a link to complete the request form at the end of our series today, or contact the America Makes TRX webinar series administrator, Jason Thomas, directly. A few important notes before we kick off the series. At the end of the presentation, there will be an opportunity for a brief question and answer session. So if during the presentation you do have a question, please submit it in the Q&A space on your WebEx screen, and I'll ask it during the Q&A session. I will do my best to get to all of the questions. Today's webinar is on grain boundary engineering for additive manufacturing. Without further ado, it is my pleasure to introduce Dr. Rashid Miraj from Alpha Star Corp. Dr. Miraj has been practicing engineering for almost 4 decades and has worked in academia, civil infrastructure, automotive, aerospace, and the defense sectors. Surprisingly, all activities have been on the cutting edge of technology, including ship design, real-time control, robotics, simulation, computational modeling, crash analysis, advanced composite design, and material characterization and testing. The common thread throughout has been the efficient utilization of materials and personnel to achieve optimal results on time and on budget. The resulting experience has allowed Dr. Miraj to appreciate the synergy of engineering and the business fundamentals that drive it. Accordingly, Dr. Miraj has developed an acute eye for opportunities both in the long term and short term through research, collaboration, and direct market sales, which has been supplemented by an innovative sense of marketing, outreach, branding, positioning, and packaging. As a result, Dr. Miraj is best suited to merge technology with the bottom line for Alpha corporate growth and stability. Dr. Miraj earned his bachelor's in mathematics from the University of Maryland, College Park. He has a master's in mechanical engineering from Columbia University in New York and a PhD in mechanical engineering from the George Washington University, Washington, D.C. He has authored numerous reports and publication and is active with outreach to universities and colleges. Dr. Miraj, I will now turn it over to you and your team. Dr. Miraj, I think you might be on mute.
On mute.
Okay, you go. I hear you fine.
Can you hear me now?
Yes, sir.
All right, sorry about that. Today's presentation is entitled Grain Boundary Engineering for Additive Manufacturing and corresponds to research conducted by Alpha Star in collaboration with the University of Southern California, the University of Michigan, and General Electric Global Research Center. This research was sponsored by the Defense Logistics Agency as part of a Phase 1 SBIR program. Grain boundary engineering is the practice of obtaining microstructures with a high fraction of boundaries with desirable properties. In general, grain boundary engineering consists of repeated cycles of deformation and annealing that result in materials and components that meet high standards of quality and performance. Now, this is not a new subject. Generations of Japanese craftsmen and craftswomen use traditional metalwork skills like smelting, forging, annealing, hardening, and polishing to produce swords of the highest quality. GE understood this and developed an AM methodology to increase the strength of stainless steel with the help of post-build heat treatment. The purpose of this research has been to duplicate the success of GE and then expand upon it. To do that, we've developed multiple new deep physics modules and combined them with the power of ICME technology to achieve grain boundary engineering for the additive world. Did you change the page? Thank you. So what problems will be addressed, what objectives secured, and what solution employed? As we all know, AM metals exhibit cracks, low toughness, low plasticity, high residual stresses, and sometimes problems with weldability. Our goal is to improve build quality and performance by varying the AM process, triggering the creation of precipitates, employing cooling strategies, exploring the use of inclusions, all the while considering the effective defects to secure preferred microstructures. Our solution seeks to supplement ICME technology with critical modules that address melt pool engineering, grain boundary engineering, phase change, diffusional creep, global local models, and material characterization and qualification. Tools will optimize grain boundaries, formulate alloy designs, improve microstructure, and identify process parameters to build quality parts. Well, how will this be possible? Well, I'm glad you asked that question. The ICME tool will accurately predict AM build outcomes, including effects of defects. EBSD Visualization software will capture microstructure. Voids and other anomalies will be evaluated. Grains and grain boundaries will be assessed. The impact on quality and life will be quantified. In parallel, an ideal solution path will be defined, including optimized parameters, build plan, cooling protocol, precipitate generation, inclusion identification. In this manner, critical concerns will be mitigated. Accordingly, ICME tools may be used to optimize grain boundaries to improve part microstructure, quality, and performance. So what's the role of ICME in this process? Okay, let's say this one more time. ICME will provide the framework and integrated platform to support melt pool engineering, grain boundary engineering, and material characterization, which will allow engineers to consider grain size and grain boundaries, virtually conduct the build, identify defects and causes of defects, visualize the microstructure, explore options to address microstructure, i.e. alter the print path, add nano or microparticles, to ultimately modify an alloy design and to find the right solution. The good news is that we are not alone. Experience has shown that ductility and toughness can be addressed by phosphorus and sulfur, durability by chromium, bonding and diffusion by nickel, and there are many more options in the toy box to get the results we'd like. New alloy composition and design would include the effective powder composition, size and distribution on microstructure, effective inclusions on polycrystalline material, and desired improvement of material properties and performance, even fracture and fatigue. The box at the bottom of the page captures the AM ICME approach and what will be manipulated by tools for grain boundary engineering and new alloy design. As you can see, we can manipulate the print path. We can explore thermal transport, including the development of process maps and the impact of not only inclusions and precipitates, but post-heat treatment, and in some cases, in situ heat treatment. The material characterization and qualification analysis not only allows us in real time to see the stress and strain of our modifications, but also use that as a point for optimization. The EBSD visualization tool allows us to see the grain boundary modifications, understand crystallization, elongation, and orientation. And also additional diffusional crack modules allow us to impact and understand crack growth, crack propagation, impacts on residual stress. And finally, the AM tool will allow us to see post-build heat treatments and the impact of roughness and other factors on the overall build. The reference method are applied individually. Excuse me, can you go back? Thank you. Oops, go back 2 pages. Thank you. The reference methods are applied individually and in collaboration with each other, which sounds like optimization. ICME supported sensitivity analysis and design of experimentation will work to identify an ideal combination if it exists. Solutions may be optimized for strength, strain, roughness, density, toughness, fatigue, and machine parameters. from net shape and warpage all the way to alloy design. Thank you. Most defects resulting from AM processes are related to thermal behavior. Swelling, keyholes, humping, unfused, balling, delamination are all common concerns related to AM metal. Our thermal management module, TNG, which has been validated for titanium, can predict the dynamic evolution of the melt pool in terms of depth, width, and length. TNG predicts thermal history, thermal state, and material state, and visualizes the heat-affected zone. The tool can be used to define a dynamic process map that relates balling, humping, keyhole, unfused powder, no melting, incomplete melting, overheating, to laser power and speed settings, or other critical parameters. That process map is shown on the right, and it shows the areas that are stable and unstable in terms of those process parameter settings. In the current example, the zones of stabilities and instabilities were validated for a single track of laser moving at different power and scan speed settings. ICMA tools predict manufacturing anomalies and the effect of those defects, as well as identify solutions. Please continue. ICO thermal management and melt pool engineering exploits the microthermal transport of steel. The thermal history of the three different steels are presented on this slide. Stainless steel 316, based on the GE patent, Morphology steel, based on the Damascus steel template, talked about by a long time ago by Mr. Ashby, and our ICME optimized steel design. As you can see, the GE patent strove for improved strain. Historically, Damascus steel is always explored or driven by the desire for increased strength. Our proposed optimized design tries to grab the best of both worlds based on the strategy we just laid out in previous slides. When reviewing the thermal history, the highest temperature for GE stainless steel is 3,102 degrees Celsius and 2,000 degrees for Morphology steel. The silicon oxide precipitate in the GE stainless has an exothermic effect on the thermal process. The martensite in the Morphology steel has an endothermal effect, which causes the temperature to be lower. From the histogram, it can be seen 36% of the powder remains unfused for the Morphology as a consequence of the endothermic effect of martensite, which takes out all the heat and does not allow the cooled powders to join or fuse together. For the GE stainless, the percentage of unfused powder is almost zero. This is because of the exothermic effect of silicon oxide, which provides the heat to melt and fuse the powder. The uniqueness of this exothermic effect is free heat to be used in an engineering manner. Inclusions also have an effect. The current example, chromium, constitutes 23% of elements for GE stainless steel and 3% for Morphology steel. Chromium elements absorb the maximum temperature, impacting the fusion. Similarly, the presence of voids contributes to the differences in thermal conductivity between the various steels. Now consider the recipe for the proposed steel. If you look to the right, you can see inclusions, you can see precipitates, as I like to say, everything plus the kitchen sink. Material composition, including precipitates and inclusion, impacts the ultimate thermal profile. ICME prediction and validation of the thermal state, material state, and mechanical strength. Recall the void distribution between the three states, which was a function of fused and unfused powders, and the effect of precipitates and inclusions. Not surprisingly, the same components impact the stress-strain curves for all three systems. This slide presents the predicted stress-strain curve of the GE stainless steel after thermal heat treatment, stress relief at 650 degrees Celsius for 2 hours, of the Morphology steel, which consisted of internal heat transfer or heat treatment, inherent, thank you, and the optimized steel option, which does not involve heat treatment. It should be noted that the heat treatment for GE stainless steel improved the strain, but only had a slight improvement of strength. In the case of maraging steel, the inherent heat treatment improved the microstructure and increased the strength, but not the strain. Preliminary investigation with the optimized alloy resulted in an increased strength and an increased strain without heat treatment. The results need to be validated against tests, but the research clearly is moving in the right direction. And so, the combinations of inclusions, the combinations of precipitation, and selective use of the process of print processing can also produce the desired grain boundary effects. New steel composition, better strength and strain, eliminate the need for post-heat treatment. Validation of fracture and fatigue crack growth properties for GE stainless steel. This slide presents the fracture property prediction of the GE stainless steel based on the post-build heat treatment. The ICME methodology for prediction of fracture toughness per thickness and fatigue crack growth is ultimately derived from stress-strain curves. So on the left, you can see the stress-strain curve for that particular GE steel. And now we're going to use that, using that fracture toughness per thickness methodology to predict fracture toughness and ultimately predict fatigue crack growth rate. The central image shows the experimental test results of Sharpie impact tests. In the experiments, the fracture energy for a specimen with a thickness of 10 millimeters was 124 joules. In that case, the numerical predicted fracture energy is very well matched with the test data and the prediction. So if you look in the central image, you can see the simulation or the prediction was 124 joules, and the test itself was also 124 joules, showing very good agreement. The image on the far right is the prediction for fatigue crack growth rate. We can have confidence in this approach based on the validated results achieved with S420M steel below. As you can see, the image on the lower right is that fatigue crack growth rate prediction compared to test. And so we had very good agreement with test, and we're able to not only see the curve, but actually compare it to points of crack growth on a physical panel. In sum, we are confident that our assumptions for not only fracture toughness prediction and fatigue crack growth rate will be applicable and will be validated. ICME tools utilize stress strain curves to predict fracture toughness per thickness and fatigue crack growth rates. Please go ahead and change. Thank you. General 3DP melt pool, addressing a dog bone, thermal transport, and defects in stainless steel. A thermal management analysis is also performed on a macro level scale LVPF printed dog bone sample made of stainless steel. The model size was 25 by 6.3 by 0.8 millimeters and included 1,197,000 elements and 20 layers. The figure on the upper left shows the build volume and thermal profile of the dog bone specimen with fused and unfused powder in the bottom plate clearly displayed. The upper right image is the histogram of the as-built specimen and highlights the composition of the material, including precipitates and inclusions corresponding to the GE stainless steel. As you can see at the top right, the presence of the silicon oxide and the chromium. The bottom right and the right and bottom middle show the macro and micro void content of the virtual dog bone specimen as built. Finally, the image on the bottom left provides a prediction of thermal conductivity of the dog bone at the end of the printing process. The significance is that ICME tools predicts melt pool, material composition, macro and micro voids, and other critical properties such as thermal conductivity. TMG with EBSD Visualization to drive grain boundary orientation. This slide lays out what is possible by combining our ICME thermal management software TMG, with the EBSD Innovation Toolset developed by the University of Michigan. Considering the heat-affected zone in the upper left, TMG actually reflects the thermal history, thermal state, and material state of the build. In this manner, TMG can establish a process map in terms of power and speed, which identifies stable and unstable configurations of the build matrix and corresponding melt pool. Here, build analysis corresponded to a power setting of 400 watts and a speed of 400 millimeters per second. With this configuration, the TMG is used to calculate laser spot size and corresponding material flow paths in support of the melt pool throughout the heat-affected zone. The EBSD visualization software can generate three-dimensional images of this experimental process. Grain boundary misorientation angle from 0 to 62 degrees is shown in the upper right, and grain orientation cross-sectional analysis is depicted in the lower right. The combined technology provides an ability to virtually explore, visualize, and ultimately optimize the impact of melt pool engineering and grain boundary engineering on an alloy or part under development. In this manner, you can eliminate or reduce time associated with scanning electron microscopy by utilizing an ICME 3D microstructure reconstruction based on the EBSD visualization. Thank you. Effective laser power and scan speed on texture. It's noted that grain size increases as speed decreases and power increases. Employing our visualization technique, we're able to change power and speed settings related to a virtual build and see the corresponding changes to the grain boundaries, and textures as related to the low-angle grain boundaries and high-angle grain boundaries. If you look at the image on the left, you can clearly see that the changes in power and speed have an obvious and clear effect. The presence of the grains, and they're all aligned in a particular direction. Our EBSD visualization tool allows us to do the same thing virtually. In this case, not only are we seeing grain angles, but we're also seeing the impact of power and speed on textures. In the lower quadrant, on the lower right-hand side, the same capability is accessible for a coincident site lattice's grains, where the coincident site lattice is impacted by variations in power and speed. Here, the small black lines correspond to the actual coincident site lattice grains. And as you can see on the lower left, grain boundary sliding and rotation also can occur in multiple levels. The higher number of CSL boundaries at low power and high speed are related to recrystallized texture at low energy densities. Ultimately, improved strain by design of grain orientation is shown by EBSD visualization. What we're trying to emphasize is these collection of modules allow you to see each component of the process and then optimize based on that individual visualization. This table brings together not only the global-local analysis of the problem, but taking global-local to identify the impact of crack propagation and surface roughness. The local model is a finite element model which is augmented by our TRX crack code, which effectively uses multi-axis remaining creep ductility approach to predict the growth of voids and precipitates in the microstructural grain boundary structure. As you can see on the left, we have an actual mount ring, and this image right next to it is the virtual full mount ring, which is subjected to temperature changes and the overall behavior. That global information is transferred to our local model, and then running a localized finite element, actual finite element analysis with the detailed shell elements for that grain, we can then predict the impact of global behavior on local behavior, and then translate that into grain boundary damage, residual stress, and surface roughness. As you can see on the image on the left, far left, bottom left, we're predicting from this global local analysis, grain and grain boundary damage. The image in the center, again, looking at that grain, can predict residual stress, biaxial stress. And finally, for triaxial stresses, we can then predict surface roughness. Ultimately, ICME diffusional creep supports the print process. You can go ahead. So now we're getting to grain boundary morphology and cracks and growth. You're taking that story you saw on the previous slide, and we're actually applying it to how it impacts overall behavior. In this particular case, we're looking at stainless steel. As you can see on the right-hand side, these are mixed, irregular, and elongated grains at a temperature of 550 degrees Celsius. Now, if we did analysis without voids, you can see that the life of the part or the life of the component is 1,100 hours. With only an increase of voids at 1%, the life is reduced to 8,000 hours. And you can see in the animation the widespread propagation of that crack. Now, with the incorporation of precipitates, as you can see on the right-hand side, if you can see them slowly to be red dots, you can see the precipitates act to control that process and control the crack propagation such that the life actually is extended to 13,500 hours. Again, careful understanding of the voids, careful utilization of precipitates and inclusions can extend useful life. ICMA tools predict 1% voids, which cause the 30% reduction in life, and in the same manner, ICMA tools can predict the consequence of utilization of precipitates and inclusions to extend that life. You're good. Thank you. Thank you. This is the AM fabrication and then non-destructive evaluation assessment, which was undertaken in parallel with our program. For the most part, we've talked about computational tools and other modules, which are predicting events. Everything we do is tested and validated in the laboratory. This program is still in its infancy with a lot more work to go, but we've been supported by our partners at the University of Southern California and the University of Michigan to not only help us with visualization tools and predictions, but also to support in testing. And as you can see in this particular case, we printed 25 specimens with the power and they were actually 20 layers thick. Each layer was, I believe, 40 microns, so the total height was about 0.8 millimeters. Of the 32 specimens, or of the specimens, 12 were subjected to heat treatment at 650 degrees Celsius for 2 hours. Of that, 4 were air-cooled and 4 were air-quenched. We were able to not only test these and collect the data, but also to see the impact of the quenching, cooling, all the various applications to the tensile test behavior, the stress strain curve, and the performance of the materials. Not only did we measure tensile test as built, tensile test is water cooled, you can see there's slight variations. Again, more testing needs to be undertaken. We need to translate what we learned virtually and correspond to what we will find through physical experimentation to update our knowledge and update our solution. In the lower left, you can see that even roughness varied with time. The measurements for surface roughness were indicated for before heat treatment and after heat treatment, and we also use scanning electron microscopy wherever possible to show the non-heat treated items, and in this case, the circle indicates a precipitate in that overall structure. Ultimately, we can say ICME qualitative prediction compares well with test for roughness and EBSD imaging. Well, that's the conclusion of our work. Let's summarize what we have. We worked on an ICME approach was conducted for stainless steel microstructural changes and effect of nano-inclusion precipitates during the AM and after the AM process. We developed multiple modules to support this. We talked about a thermal transport model, a material characterization model, a creep diffusion model, a phase diagram model, and as you saw, an EBSD texture reconstruction technique for visualization. Lessons we learned in this process are that long grains translate to high strain, precipitates can improve strength and decrease crack propagation, residual stress increases elongation, inclusion increases both elongation and strength, voids can increase crack propagation, and hydrostatic pressure affects strength. I think a further conclusion of this is that sometimes items that you think would have a negative effect, if properly organized with other considerations, can have a positive effect. That's why bringing the ICMA tool to understand the overall process and optimizing that can help you find the best solution among a large variety of options. Our next steps are to continue the validation of the ICMA tool and explore the behavior with other material systems, including Inconel and aluminum alloys. Thank you very much for your time, and I'd be happy to answer questions that you may have going forward.
All right, thank you, Dr. Mirage. We'll now head into the Q&A session. Once again, if you have a question for the presenter and you haven't done so already, please type it into the chat box. I do have a few questions that have come in. Let's go with the first one here. You've made multiple references to precipitates. Are there good and bad precipitates?
Certainly. Precipitates can have a consequence where they can improve the overall performance of the material system, and they can also have a detrimental effect. The question is more of the careful application and selection of those methods.
There are good precipitates, bad precipitates, and precipitates and effect. So the good precipitates are like martensite during cooling, past cooling process that would increase the strength. Bad precipitates like zirconium oxide that causes cracks initiate. Medium precipitates is during printing process. That means you're creating, in the case of the steel, pearlite, bentonite that has no effect, or due to medium cracks of cooling, you create ferrite, which improves it a little bit. So they can hurt you, can hurt the final performance, or can help it. So that has to be designed very carefully during the thermal additive manufacturing process.
All right, thank you. Another question we got here. What heat treatment was applied to the merging steel?
The merging steel, they call it inherent heat treatment. It means that we would apply during the laser process, printing process, we call it hard and soft layers. So for example, we fix the laser machine parameters for 4 layers, and then we stop and then cool it down due to gas for fast, like hydrogen or nitrogen or helium, to cool it down for 30 seconds, 60 seconds, 90 seconds, and 180 seconds. That would give you that precipitate, the good precipitate that the martensite is for. So this process does not require post-heat treatment at all. And that's the saving time and effort to maximize your printing time and minimize your post-heat treatment.
All right, thank you. So we've got another one here. What is the difference between a low angle grain boundary and a high angle grain boundary?
That's a good question. Low angle grain boundaries like a zebra colors, the animal, these are formed during when the element recrystallizes during thermal heating or forging process that you heat the material. These are formed relative to grains relative to each other, and they break. And then if the angle is between 0 to 15 degrees, that would be in parallel with the process the machine is taking, and that would give you a ultimate strength and plasticity, similar to samurai sword, that they're trying to achieve maximum strength. The high angle grain boundary, these are the equiax grains that hex type, and then when you are resistant, they are resistant to formation of precipitates. They break, but they would resist, and then that would not give you the highest strength that you're looking at plasticity, but only give you the CSL grain, which is the grains are broken to crystallize, and then they can rotate and give you additional the deformation and plasticity. So that's called equiax channeling. You punch the material the same way they do it in the samurai sword and Damascus steel, by punching it during the very high heat. The material is molten and you're hitting it. So we're trying to duplicate that process, learning from samurai steel and Damascus steel the last 5,000 years to bring it to additive manufacturing and then create the science with that to satisfy the products that are being developed for applications such as high turbine engine application.
All right, thank you very much. That's all the time we have for questions today. So if you do have any additional questions, you can always reach out to AlphaStar directly via info@alphastarcorp.com. Any of the questions that were sent in that I did not get to today, I will send to our presenter and have them respond to you. So that will wrap up today's TRX webinar series. I would like to once again thank Dr. Rashid Miraj. If you do have further questions for Dr. Miraj, like I said, you can reach out to them directly via info@alphastarcorp.com. There will be a post-webinar survey going out to all those who participated. We do really appreciate the time that you take to provide America Makes feedback so that we may continue to improve and strengthen the additive community. And as a reminder, if you think that you or your organization will be interested in sharing on the TRX webinar series, you can fill out the form that follows on our website, or you can reach out to myself, Jason Thomas, directly at jason.thomas@ncdmm.org. Thank you very much, and everyone have a great day.